Okay, so welcome back to another session. Thanks for joining me tonight. There's not as many of you guys on tonight, but that's all right. Like I said, just more opportunities for you to ask me questions. So let's take a look at our first couple of problems here. So I'll kind of zoom in on that first problem and see what we're looking at. So here we are looking at a box where there's only red pens, blue pens, black pens, and green pens. So four different colors. And we've got the probabilities that the pen will be red or it will be green. So we've got our probability for red is 0.42 and our probability for green is 0.14. So we can think of those as percentages if we'd like. And then it says that the probability that the pen will be black is three times the probability the pen will be blue. So I'll go ahead and underline these because it's telling us some important information here. So three times the probability that it's going to be blue. There are 28 green pens in the box, and we need to figure out how many black pens altogether there's going to be. Okay, so the first step is to kind of figure out how much probability, what's our probability of getting red or green currently. So we have the 0.42 and the 0.14. So let's go ahead and add those together. I'm going to scroll over a little bit, or I'll scroll all of this over a little bit. And we'll add those together. And you want to make sure that we actually write it out so that we get the marks for our working. So we've got 0.42 plus 0.14, and that gives us 0.56. Okay, so that essentially means that 56%, or a probability of getting a red or a green pen is going to be 56% altogether, essentially, or 0.56. Now, because we know that our probability is going to add up to one, so it's going to be either red, blue, black, or green, our percentage or probability of getting one of those colors has to be 100% or one. Okay, so I'm going to subtract the 0.56 from one, and we end up with 0.44. So, what that represents is our chances of getting, in this case, blue or black. Okay, so this is basically our probability of getting blue or black. All right. So our next step is to figure out, well, what is blue and what is black represented by? And we're going to come back to this statement here. So the probability that the pen will be black is three times the probability that the pen will be blue. Well, it's going to be three times something. Well, we don't know what the probability of blue is going to be, so I'm just going to call that X. And since blue is X and black is three times this probability, it's just going to be 3X. Okay. So for us, we know that the probability altogether of blue or black is just going to be X plus 3X. So the probability of blue or black is equal to X plus 3X, which is just 4X. So from here, we can then put these two statements together. Since we know that the probability of blue or black is going to be 0.44, it also has to equal to 4x. We can state that 0.44 has to equal to 4x. We can divide both sides by 0.4, or rather not 0.4, just 4. And then we end up with x is equal to 0.11. Okay, so this implies that if I were to look at the probability of blue, it's just going to be 0.11. And then we can say the probability of black is equal to 3 times 0.11, which is 0.33. Again, we didn't really need the blue. We just wanted the probability of black here. So we are given the fact that we have 28 green pens in the box. Okay, so we're not going to work with the 0.33 just yet. We're going to figure out how many pens are in the box altogether. Okay, so if we take a look at green, we have the fact that green, the probability is 0.14. Okay, so we can say let's say let y. I'll go ahead and explain what I'm doing here. Let y equal the total number of pens in the box. Okay. So the total number of pens in the box is going to be y, but we know that 14% of the total pens has to equal to 28. So let's go and put that into an equation. So we are saying that 14%, or 0.14, of y, and maybe I'll just write it straight out like this, 0.14y has to equal to, like we said, the 28 green pens. Okay, so 0.14 has to equal to 0.14y has to equal to 28. And let's divide both sides by 0.14. So we get y is equal to 28 divided by 0.14. And we end up getting y is equal to 200 pens. Okay, so there are 200 pens all together in the box. All right, so now that we know exactly how many pens there are all together, then we can come back to our statement where 33% of our pens are black. And we can say that 0.33, or 33%, times 200. So 0.33 times 200 gives us 66 black pens. Okay. How do we do on that one? Can I get some thumbs up in the chat if we're feeling pretty good about that answer? Did we have any questions regarding that? Did anyone have a chance to try out the second one? Maybe what I'll do is I'll just put the answer on the screen. So for that second question, we should end up getting, I believe it's 18 red counters for anyone that tried it out. So 18 red counters. I'll scroll back up to this question if you guys want to take a picture of the question. So he said there are going to be 18 red counters. So you can go ahead, take a picture of that, and you can write this answer down as well. So there's 18 red counters for anyone that that had the chance to try this one out. Okay. So let's take a look at some of the topics we're going to go over today. We're going to talk about probability trees, conditional probability, and then probability equations. Again, probability trees are fairly straightforward. I think we're probably going to spend more time on conditional probability. And again, depending on how we feel about probability equations, because those ones are grade 8, 9 questions, might be a little bit trickier. It's just going to be a lot of practice. If you're not as comfortable forming and solving equations, probability equations is going to be pretty difficult. But again, we'll see how much time we have and where we get up to. So starting off with our first example with probability trees, I'll go ahead. I'll let you guys take a look at this question and maybe and get a head start here. So you got our friend Tina. She has 2 bags of counters, bag A and bag B. There are 5 red counters and 3 blue counters in bag A, and there's 4 red counters and 5 blue counters in bag B. Tina takes a random counter from each bag. Let's get rid of that random article there. Takes a random counter from each bag. You want to first draw a probability tree to represent the information, and then work out the probability that she takes 2 blue counters. So I'll give you a second there just to kind of get a feel for what the question's asking, and maybe make your own little sketch of what you think is happening with that probability tree, and then we'll take a look. So I'll give you about a minute there just to get started, and we are going to amp up the difficulty in the questions as we go along, but just something nice and easy to start us off. Okay, so let's see what we've got here. So to start things off, we just need to recognize that we have 2 bags. We have bag A and bag B. So our probability tree is going to get split into 2 sections essentially. So first, we're going to start off with bag A. And in bag A, there are 2 routes that we're going to take, where it's either going to be a red counter or it's going to be a blue counter. Maybe I'll do this on the side here. So if I get a red counter, our probability of getting red in bag A is going to be 5 out of 8 total. So we get 5 over 8 as our first probability there. And our second possible option is a blue counter, which we can see we're going to have 3 out of 8 altogether. Moving on to bag B, and maybe I'll just make this a little bit smaller. And what that's going to look like is depending on whichever branch we go into. So let's say the first branch, we pick a red counter. Then from bag B, and maybe I'll write it up here, bag B, it's either going to be, again, red or blue. But because our number of counters is different, we can now write our second stage as 4 out of 9 for bag B is going to be red, and then 5 out of 9 is going to be blue. Again, looking down at bag B after you have chosen a blue counter from the first bag. Again, looking at either red or blue. Let's go ahead. Red or blue, it's still going to be 4 out of 9 or 5 out of 9. Okay, so that's the first part checked off. So we've drawn that probability tree to represent the information. Next, we want to be able to figure out the probability that Tina takes 2 blue counters. Okay, so here is the main part that essentially confuses students. When do you multiply and when do you add things together? Okay, so essentially we're taking a look at 2 keywords. So the word or, okay, or means that you're going to add the probabilities. Okay, and basically these events cannot happen at the same time. And then the other option, if we see the word and, you're going to multiply them. So we want to multiply the probabilities. Okay, and basically our events are happening consecutively or one after another, or rather, what's the word I'm looking for? Simultaneously, or one after another. Okay, or consecutively. So simultaneously or consecutively. I'm forgetting my words tonight. Okay, so if you see or, you're going to add them, and if you see and, then it's going to be multiplying. Now, with this type of problem here, it says that Tina takes 2 blue counters, okay? So we can think of this as, well, Tina's going to get a blue, and then she's going to get another blue, okay? So, and then she's going to get another blue. So first a blue, and then another blue, okay? So that means in this case, we're going to be looking at multiplying our probabilities, okay? So hopefully that explanation makes sense. So again, we're going to figure out the probability of blue and blue. Okay, so in this case, we're going to figure out which branch we're going down. So we're going down this first branch. So we see that we have 3 over 8. And then we're going to go down the second branch, and then we see that we have 5 over 9. So our probability of blue and blue is equal to 3 over 8 times 5 over 9. Remember, when we multiply fractions, we multiply across the top, multiply across the bottom, and that gives me 15 over 72. I think we can simplify this. We can divide both sides by 3, and we end up with 5 over, I want to say 24. Okay, so 5 over 24 ends up being our probability there. Again, it doesn't say to simplify, but we just want to make it look nice. Okay, so our 15 out of 72, or 5 over 24. All right, any questions about how I did that first one? So again, I would say the key here is just to walk yourself through your probability tree. Does your probability tree make sense? Do you recognize if it's an or an and situation? All right. Okay, so I want you guys to go ahead, try this one out on your own. So it's very similar to this one. Some of you guys might find it pretty straightforward. So I'll give you about a minute or two only just to try this one out. And then we're going to take a look at a more difficult example using the probability tree here. And again, just to give me an idea of how we're finding things, is this too easy, too hard, or just right? You guys can just let me know in the chat here, just so I can kind of gauge what the level of this group is looking like. Maybe a bit easy. Yeah, fair enough. So what I'll do maybe is if you guys decide to take a picture of this, I'll just quickly put answer key for this on the screen. And then that way we can just kind of move on to the next section here. So again, a lot of the questions that I get, I just kind of pull straight from Math Genie. Great resource that you guys should be taking a look at and utilizing as much as possible. So I'll toss the answer up here on the screen. I'll shrink it down a little bit. And then we'll kind of go really quickly through one harder example of probability trees and then get to the grade 7 conditional probability here. So you can see we have our two sections or two stages of our probability tree, and the probability that she wins both games is just going to be winning the first chess game and then winning the backgammon game. So 0.6 times 0.7. So she wins and then she wins. So giving us 0.42. Okay. So our next example here is going to be one with our friend Paul. Okay, whoops. I accidentally put the answers up on the screen there. So we got a picture. No, that's the wrong example. Where did my example go? Sorry, give me a second here. So we're going to take a look at Paul, our friend, and he's going to wear either a black or a red tie to work. So you can see that that and or statement coming in essentially. So we can kind of get an idea of exactly which or what we should be doing with our probability. So on any day, the probability he wears a black tie is 5/9. Draw a probability tree for Monday and Tuesday, and then work out the probability that he wears different ties on Monday and Tuesday. All right, so I'll quickly work through this one. Again, we're going to have two stages where we have either Monday or Tuesday, and then we're just going to take a look at if we're multiplying, adding, or both for this one, okay? So let's start off with our Monday here. So Monday, we can see that he's either going to wear a black tie or a red tie. So it's one or the other. Okay. So if we start off with Monday, so we get Monday, and then maybe we'll do Tuesday here. So black tie is going to be 5/9, and then your red tie is going to be 4/9. And then for Tuesday, again, it's going to be either a black tie, which is 5/9, and then we get 4/9 for the red tie. And same thing here, black is 5/9 and red is 4/9. Okay, so that's the first part worked out. We want to figure out the probability that he wears different colored ties on Monday and Tuesday. Okay, so again, when we think through this problem here, we're going to start by writing out our probabilities that we want. So first, you want different colored ties on Monday and Tuesday. Okay, so first, you want the probability of, let's say, black and then red, which is just going to be 5/9 times 4/9, which is 20/81. And then we want the probability of getting red and then black, which is just going to be 4/9, again, starting down here, 4/9, and then 5/9. So because we said and, we're going to multiply those probabilities. But we can see here that he can go black and then red, or he can go he can go black and then red, or red and then black. So what we need to do with these two probabilities is to simply add them together. Okay, so 20/81 plus 20/81 gives us 40/81 as our final probability there. Okay. So hopefully that part makes sense in terms of being able to set ourselves up in terms of those and or statements. Any questions regarding probability trees? Because once we get to this point, we're just going to go ahead and start with me just assuming you know how to work through probability trees, and then we'll get going. Okay. All right. So we're going to take a look at a couple of examples to start us off. Again, I'll put two examples up on the screen just in case you're finding one a little bit too simple, and then we'll work through the first one together, give you guys a chance to look at the second one, and then we'll talk about what we've kind of come up with here. Okay. So let's put this next question up on the screen. So we've got, like I said, we're going to go into conditional probability now. So it says there are only red marbles and green marbles in a bag. There are 6 red marbles and 4 green marbles. Mason, our friend, takes a random marble from the bag, and he doesn't put the marble back in the bag. Okay, and then he takes at random a second marble from the bag. Okay, so the important thing to keep in mind here is that we are not replacing, okay, that marble. And I think what a lot of people kind of forget is that we need to keep that we want to keep that in consideration while we write out the second stage of probabilities. Okay, so we're going to look at our first marble, and we're going to again draw our probability tree here. So let's go ahead and look at our first marble. So the first marble, our probabilities. So we have 6 red marbles and 4 green marbles, which means that 6 out of 10 will be red and 4 out of 10 are going to be green. So it's going to be either red or green. And like we said, it's going to be 6 over 10 and then 4 over 10 for the green marbles. And then now we're going to take a look at the second marble. And again, if we're looking at red or green, okay, our probability is going to change depending on what we got from the first round. Okay, so the big thing that's going to change here, if we picked a red marble in the first round, there are no longer 6 red marbles left. There are now 5, but instead of having 10 marbles altogether, there are now only 9. Okay, whereas for the green marbles, we didn't change how many green marbles there are, so there's still 4. But again, we're choosing out of 9 marbles instead. Same thing for the second leg here, or our second half of our probability tree. If we picked a green marble first, that means that instead of having 4, we are now down to 3. And instead of picking out of 10, we're now picking out of 9 for that second stage. If we got I'm getting ahead of myself. That should be down here, 3 out of 9, my apologies. And then for the red, because we didn't pick red the first time, we still have 6 reds, but now we're picking out of 9 altogether. Okay. Are we all feeling okay about that idea of subtracting from the numerator and the denominator if we need to? Just taking one down each time, depending on if we picked it or not. Okay. So that's what our probability tree is going to look like. And then now what we're going to do is we can go ahead and write down our probabilities that he takes 2 marbles of the same color. Okay. So essentially, if we look at what it's asking us, we want the probability of red and red. So that means that we have 6 over 10. So we look red and then red, and maybe I'll highlight this. So red and then red. So that means we're looking at 6 over 10 times 5 over 9, which gives us 30 over 90. And I'm not going to simplify that just yet, depending on what we end up with. And we're going to end up with a denominator of 90 anyways in the second possibility. Then we want the probability of green and green. Maybe what I should do, just for a more effective practice here, we don't want to say R and R. We don't want rest and relaxation. We want red and red. And then over here, we want to say green and green, okay? Just so we don't get any marks taken off for ambiguity. So green and green is just going to be, in this case, I'll do green and green. So you have 4 over 10, and then we've got 3 over 9. So let's go ahead and write those probabilities down. So green and green, we have 4 over 10 times 3 over 9, which gives us 12 over 90. Okay. So remember what I said about the and or statements? So we've got the and statements here, which meant that we multiplied these. So it's red and red, green and green. But we're saying that what's the probability that he takes 2 marbles of the same color? So basically, we're saying that it's red and red or it's green and green. So because we are saying that it's either this or that, we're going to add these together. So the probability of both red or both green is equal to 30 over 90 plus 12 over 90. And that gives me 42 over 90. And we can simplify this to, what is that going to be? 21 over 45 or 7 over, why am I struggling with this? It is late at night. 7 over 15. There we go. 7 over 15. So 42 over 90 or 7 over 15. Okay. Any questions about how I ended up with all of this? Can I get a thumbs up in the chat if we're feeling okay about this? Okay, good. So I'll give you guys some time to work through that second one on your own. So I'll put about 2 minutes on a timer here for you to try this out. It shouldn't really be too bad. Hopefully we don't have to spend too much time on conditional probability. Maybe I'll look at one that's a little bit more difficult, and then we'll head straight to probability equations, which I'm sure you guys are going to enjoy as well. So we've got Paul here. So I'll put 2 minutes on a little timer here, and we'll see what we come up with. Okay, so I'll toss up the answer here on the screen. So we're going to end up with a probability of 0.662. Okay, so 0.662 is what he'd end up getting. So 0.662, let's go ahead and put that on here, 0.662. Can I get a thumbs up in the chat if that's what you guys ended up getting, just so I have an idea of where we're at? Okay, perfect. So what we're going to do next is we're going to take a look at our Venn diagrams here with the use of conditional probability. So we have our first little situation here. We've got 50 people were asked if they like tea, coffee, and hot chocolate. Every person likes at least one of the drinks. 17 of the people like all 3 drinks. 31 of them like hot chocolate. 34 like tea. 34 like tea and coffee. 7 of them like tea and hot chocolate, but not coffee. 2 of them like coffee and hot chocolate, but not tea. 2 of the 50 people are chosen at random. Work out the probability that they both like coffee. Okay. So let's take a look at how we're going to draw our Venn diagram. So we know we're going to have 3 circles plus what we call our universal set. So we're going to essentially put all 3 of our circles in a box. Okay. And again, this is good practice for later on when you do have numbers that are going to not quite fit into one of the circles and have to come outside the box. So let's make 3 circles here. 1, 2, and 3. So let's label this tea, coffee, and hot chocolate. So again, it doesn't really matter where you label tea, coffee, and hot chocolate. I just decided to label it like this, as long as you're kind of keeping in mind where you're putting your numbers. Okay. So typically, my advice for you guys is to find out what's in the middle. Okay. So always start in the middle if possible. And then we essentially are just going to work our way outwards. So we know that every person liked at least one of the drinks. So there's going to be nobody here that doesn't like at least one of these. Okay, so sometimes and in more difficult questions, you're going to have like one person that's going to be out here, or X number of people, or whatever is on the outside. But we're going to start in the middle at 17. So the 17 people like all three. And what we're actually going to do is we're going to skip this portion here, because remember, this 31 is going to encompass everything that's happening there. Okay, so we're not really at that point yet. So I'm just going to skip all of this section, and we're going to try to go for the ones that are more specific to the ones that are less specific. Okay, so essentially you want to go from the most specific statements to the least specific. So 7 people like tea and hot chocolate, but not coffee. So tea and hot chocolate. So tea and hot chocolate, but they don't like coffee. Okay. So 7 people are going to be in this little section because they can't be in here. They're not part of the 17 because they do not like coffee. Okay. And then we can see here that 2 of them like coffee and hot chocolate, but not tea. So hot coffee and hot chocolate, but not tea. So they're not included in the 17 here. So we get 7 and then 2. Okay. Are you all doing all right there? And then from there, we're going to start to fill in some of the rest, just based off of the numbers that we have. Okay. So we can see that we are essentially just about done with the hot chocolate here. So with the hot chocolate, we know that there are going to be 31 altogether. So if we have 31 minus 7 minus 17 minus 2, so what is that going to be? 31 minus 7 minus 17 minus 2. Again, just confirming in case I make a silly mistake, I end up getting 5 is what I'm left with. Okay, so 5 people like hot chocolate only. Okay. And from there, let's go and fill in the rest. So let's see what else we need. What else can we figure out? We know that, let's see what's going to be next here. We've got 50 people all together, 34, 21. So again, most specific to least specific, 21 people like tea and coffee. So let's go ahead and work through this one. So I'm going to do this in purple. 21 people like tea and coffee. Okay. So if 21 people like tea and coffee, okay, so that also includes the people here in the middle. Okay. So because 17 people have already said that they like tea and coffee, well, there's only going to be 4 left. So 21 minus the 17 is going to equal to 4 people left who only like tea and coffee, but not hot chocolate. Okay. So that's where that 4 comes from. And again, please make sure you write down these simple arithmetic operations again, because sometimes the mark scheme is very, very specific about what they actually see. So if they don't see the 21 minus 17, you might not actually get a mark for your work, unfortunately. Okay. From there, let's fill out the rest of this and see what else we have. So we know that 34 people like tea. So I'll do this in, let's go for a cooler color. Let's go for like a mint, a teal, cyan, whatever you want to call it. So 34 people like tea. So we can see all together, if we have 34 people who like it, we've already accounted for 4, accounted for 17, and then another 7. So what is that? 21, 28. So 6 people only like tea. Okay, so 6 people only like tea. And then the last thing that comes up is, and maybe I'll do this one in orange. There are 50 people altogether. Okay, so we're going to go 50 minus everything else in here to figure out how many people only like coffee. So 50, maybe I'll make that a little bit neater. 50 minus 6 minus 4 minus 7 minus 17 minus 2 minus 5. So I'll kind of work backwards here. 10, 27, 34, 36, 41. So 50 minus 41 is 9. So 9 people like coffee only. Okay. Are we all good with where we got those numbers from? Were there any operations here that I did that you were kind of confused or you're not sure how I knew that as a fact? No? Okay. So let's take a look at the probability that they both like coffee. All right. So we need to figure out how many people like coffee at the end of the day. So if you go and count, let's see how many people, let's highlight this actually. So how many people like coffee? So 4, 17, 2, and 9. So let's go ahead and add that up. So 4 plus, and I'll do this in black, 4 plus 17, 4 plus 17 plus 2 plus 9. So what does that get us? 11, 28 plus 4 is 32. So 32 people like coffee. Okay. So we're trying to figure out the probability that they both like coffee. Okay. So that's where the conditional probability comes in. So our first person that we choose, our probability is 32 out of 50. And then the second person that we choose is now going to be 31 out of 49. So again, it's going to be 31 because there's one less coffee person that we have. And because we've already taken out one person out of the 50, we are left with 49 for that second stage. Okay. So 32 times 31 gives us 992 over 50 times 49. 50 times 49. I realize I should have my scientific calculator with me. So 992 over 2450, we end up getting a grand total. I think it ends up being 496 over 1225. So 496 over 1225. Or if you end up just writing a decimal, we end up getting 0.405. 0.405. Again, remember that probability can be a fraction, can be a decimal, can be a percentage. Okay? Do you feel okay about this example here? And you get some thumbs up in the chat. Would we like to do a harder Venn diagram, or do you want to just move on to probability equations? This is a grade 7 topic here. Just like some input so I can kind of see where we're at. A harder diagram? Sure. Let's go with a harder one where you're going to have to figure out some more information on your own. Let's see which one's going to be harder. Let's go with Let's go with all of these. Yeah, let's go with this guy here. All right. So we got 50 people. We're now talking about fruits. I'm tired of talking about coffee. It is almost 8 p.m. It's getting late. We don't need coffee. So we got 50 people who, oops, again, put the wrong picture in there. We got 50 people who like fruits. We got apples, bananas, and oranges. Some of them like all three fruits. Some of them don't like any of them. So I'll give you guys a second here to quickly run through this one. This one might still be a little bit too easy, actually. So I might try to look for something slightly harder because I think you guys might find that one potentially still not hard enough. So I'll give you guys a minute there to try that out. And then once you guys are done, you can go ahead and put your answer into the chat just so I can see where you guys got up to. And I think I'm actually going to give you guys one harder example that I just found. And then I'll put that on there as well. So for anyone that's done with that one, we end up getting 58 over 175. So 58 over 175 ends up being our answer for this one. Again, if you aren't quite finished, that's okay. I'll give you a second there just to kind of mull that one over. And then I've put up a second problem here on the side as well. So I'll give you a second to read through that second one, and maybe let me know in the chat what we're finding the most difficult about that question, because there might be some of the notation that you might not quite remember. All right. So maybe while you guys kind of work through that second one here, I just want to touch really briefly on this first part. I think the only real part that you'll have troubles with in this second example is this little line right there. We have n of c with the upside down u, that is the intersection notation, with the union of s. Okay, so basically what this little sentence is saying, that we want the number of elements. So elements is just just a fancy way of saying number of boys in this case, who happen to like. So number of boys in the intersection of curry and pizza. In the intersection, so number of elements in the intersection of curry and pizza, and the union with the number of elements in the number of boys who like spaghetti. Who like, oh, my handwriting is atrocious tonight. Who like spaghetti. Okay, so pretty much if I were to visualize what's happening here, okay, so let's go ahead and draw curry, pizza, and spaghetti. So we got curry, pizza, and spaghetti. We want, first of all, to, maybe I'll do this in a slightly different color. Let's highlight this again. So the intersection of C and P. So they must like both curry and pizza. So that's going to be this section here. And that's also going to be this section here as well. Okay, they like curry and pizza in both these sections. But we're also going to include the union of set S. Okay, so everything that's within this circle as well. Okay, so basically all of those sections, whatever numbers are in those sections, is what we're going to add together. So in this case, it ends up being, I think, 34. Okay, it ends up being 34. And then if you're able to confirm, just give me a thumbs up in the chat. That's what you guys got. Okay, good. And then it says the probability that the boy selected at random only likes curry. We end up getting 5 over 49, or 5 out of 49. So it's 5 over 49. And then the probability that a boy selected at random likes curry, given that he likes pizza, is going to be, if I take a look, what do we get for the answer? 7 over 13. Okay, so 7 over 13. Okay, so we're going to move on to probability equations. So we'll do this just as a quick little. So n means the number of elements, and the u is the union. So basically think of everything that is either in this one or that one. So for example, if I were to say, if I were to maybe do A union B, so that means that I can look at everything in A, but because it's now in a union with B, so we're looking at everything in there. So we're pretty much counting all of the things that I've highlighted, either yellow or blue. Okay, versus if I were to do something like this, if I said A intersection B, so if I have A intersection B, it's going to be only the things here in the middle. Okay, because whatever we're looking for, the elements that we're looking for has to be in A and it has to be in B. Okay, excellent. So let's look at maybe one or two examples of, excuse me, probability equations, and then we will call it an evening here. So starting us off with the first example, let's do something relatively straightforward to start us off. And then maybe for the second example, we'll do something a little bit more difficult. And I'll link you guys to some extra practice here. So our first question talks again, you guessed it, about some counters. So we've got some counters. We've got some red and blue counters in a bag. And the ratio of red counters to blue counters is going to be 3-1. Two of the counters are removed at random. The probability that both the counters taken are blue is 1/20. Work out how many counters were in the bag before any counters were removed. Okay. So before I get started, I'm just going to give you guys a chance to think about what this question is asking, because it's not readily apparent right from the start where we're going to take this. We've got a little bit of ratio. We've got things being removed. We're given a probability already that of one of the branches is going to be 1/20. Figure out how many counters there were altogether before anything's removed. Okay, so I'll give you guys about a minute there, and we want to figure out what can we do to get started. Okay, what can we do? Because there's lots of information here, and I think the hardest part is figuring out what's our first step. What do we need to kind of key in on? Because I can definitely see some of you guys looking at a question like this and you're like, oh, I have no idea where to start. So let's take a minute, figure out, where do we start? What's going to be important? How do I work through this question? Okay, so what do we think? What's our first step going to be when we're looking at this question? How are we going to use the information that's given to help us out? All right, we're feeling a little bit shy, so I'll help you guys out here. So since we have a ratio, okay, remember the ratio, what it does is it tells us, it gives us an idea of exactly the ratio of one color to another. So in this case, it's going to be 3-1. Okay. It doesn't really matter how many counters there are. We just know that the ratio is going to be 3-1. So we can start off by just simply writing that the number of red counters is going to be equal to, and maybe what I'll start off as the blue number of blue counters. Number of blue counters is just going to be X. Okay. Because we can see here that one part we can represent as X, and we're going to compare this to three parts, which is going to be red. So we have X counters are going to be blue, and 3 times the number of blue is just simply 3X. Okay, so hopefully that part makes sense, just using our ratio here. Okay, so that means that our total number is just going to be X plus 3X, which is 4X. All right. Are we all happy with that start? Okay, because that's going to set us up here for the probability tree that we're going to make. Okay. So starting us off, we're going to start us off by removing a counter after looking at the probability of red or blue. So if we're looking at first off our first stage, so our first counter that we're going to choose, it has to be either red or blue. And we can see here that our probability of getting red is 3x out of 4x, because our total is 4x. And if we look at the blue, it's just going to be x out of 3x. And we're not, or sorry, x out of 4x rather. X, excuse me, x out of 4x. Okay. And then the second marble or second counter that we're going to remove, before we can do that, we're actually going to remove two counters at random. Okay, so we're going to remove two counters at random, but we don't know, we don't really know which counter is going to be removed, but we're just going to remove one counter. Okay, so this is where it gets confusing, or it can be confusing. So let's imagine that we picked our first red counter. We picked a red counter first. So, excuse me, we picked a red counter first. So we no longer have 3x counters. We have 3x minus 1. So now this is the second stage. We have 3x minus 1 counters, or 3x minus 1 red counters, out of 4x counters. But because we took one out, it's now going to be 4x minus 1. Okay. If we take a look at our blue counters, we still have x counters. Okay, we still have x counters because we didn't take out a blue one yet. But now, because we removed one of these counters at random, it's now going to be x over 4x minus 1. Okay, so x out of 4x minus 1. And we can do the same thing down here at the bottom, where now we're going to pick either red or blue after getting blue. And if our first counter was blue, then we still have 3x counters out of 4x minus 1 because we've taken one away from 4x. And down here at the bottom, because we've taken out a blue, we no longer have x counters. It's now x minus 1 divided by 4x minus 1. Okay. Now, the last piece of information that's going to be very relevant to us, and this is where why we call it a probability equation, is that we actually get one of these probabilities at the very end of the tree. Okay, probability at the end of one of these branches, it tells us the probability that both are blue is 1 over 20. So both of these being 1 over blue, or being blue, is 1 over 20. Okay, so I'm going to go ahead and write that down at the end. So this is going to be 1 over 20. Now, remember what we said earlier. If we said that we're going to have blue and then blue, we're going to multiply our probabilities together. Okay, so we're going to multiply these together. What that does for us, and maybe what I'll do is I'll move this over, is we'll end up having x over 4x times x minus 1 over 4x minus 1 has to equal to 1 over 20. Okay? So hopefully we understand where that came from. We have to multiply those together because, right, those two probabilities have to multiply to give us 1 over 20. And now you're probably thinking, oh no, we're going to work with some quadratics. Not necessarily, right? Because now this is where we can start to get rid of some of our variables. X divided by x is just going to be 1/4. So I have 1/4, and maybe I'll do that in blue here. So 1/4, because 1 is going to be left over, 1 over 4 times x minus 1 over 4x minus 1 will look like this. And this is going to be equal to 1 over 20. And when I multiply these, I can expand my brackets. So if you want to write it like this, 1 times x minus 1 over 4 times 4x minus 1, perfectly fine. You can do it just like that. We'll expand our brackets. So we'll have x minus 1 over 16x minus 4 is equal to 1 over 20. Okay. And let's go ahead and, again, depending on how you like to interpret this, I like to cross multiply. So what that means is I'm going to multiply this up over here, and I'm going to multiply this up onto this side. So that gives me 20 times x minus 1, and that equals to 1 times 16x minus 4. So we end up with 20x minus 20 is equal to 16x minus 4. And from here, it becomes a pretty straightforward linear equation that we're going to solve. We're going to make x the subject. So I will subtract 16x from both sides first. We'll end up with 4x minus 20 is equal to negative 4. Let's add 20 to both sides. So plus 20 plus 20. We get 4x is equal to 16. And then finally divide both sides by 4. And we get x is equal to 4. But let's see what the question actually is asking. How many counters were in the bag before any counters were removed? Okay, so we need to figure out how many counters were in the bag. Well, because we know that x is equal to 4, we're going to go back up to this portion up here, way back at the beginning. So the total number is equal to 4x. But because we know that we have 4 times 4, we have 16 counters in total. Okay. So the hardest part from this portion is really just setting up your probability tree. It looks really, really complicated. But really what we need to do is just keep our head straight, understand exactly what we're working with. We're going to subtract or add whatever the question is asking us to do in the right spots. And we're going to reevaluate and make sure that we understand what steps we've taken. Do those steps make sense? Can we progress through the problem? Okay. Okay. I will give you guys one more question to work on. Okay. This is going to be a little bit trickier than the one that we've just done. If you got to go, please feel free to do so. I'll work through this one before I call it a day myself. So I'll give you guys this one to try out. I'll give you a few minutes. So let's go ahead. I'll put this one up on the screen. I'll give you a few minutes to try this out on your own first. So this question is definitely worth working through, especially if you are aiming for a 9. This combines just counting through it. We've got 1, 2, 3, 4, 5 different concepts all sprinkled throughout the GCSE level. So this is actually a fantastic question to make sure you really know your stuff if you're chasing that 8 or 9. Yeah. So let's start off by kind of considering what we're working with first. How many total counters do we have? Okay. So we know that we have 5 red counters. So we got 5 red counters and we've got Y blue counters. Okay. So let's go ahead and let's reiterate 5 red, Y blue. So that means that our total is just going to be 5 plus Y. Okay, does that make sense? So our total number is just going to be 5 plus Y, and that might have been where you guys got stuck first. Okay. So now Imogen is taking a counter from the bag at random, and then she's going to put it back into the bag. Okay, so just make sure you don't forget this part. She does put it back into the bag, which actually makes this question slightly easier, slightly harder, depending on how you look at it. right? Because you might think that you're going to add or subtract something. And then she's going to take another random counter from the bag. All right. So let's actually start off with that. So we can look at the first counter and then the second counter. Okay. So the first counter, it's going to be, let's say it's red versus blue. So our first probability, if it's red, there's 5 red out of 5 plus y counters, right? So 5 out of the total. For blue, it's going to be y out of the total, right? Does that part make sense? Now for the second leg, does anything change? Yes or no? Or does it stay the same? What are we thinking? It stays the same. Yeah, exactly. If you put the counter back into the bag, right, we're not changing our probabilities. So again, we're looking at red and we're looking at blue at being exactly the same. 5 over 5 plus y. And this will be y over 5 plus y. Okay, so they stay the same. Nothing changes. All right. So again, we're just talking ourselves through it. Doesn't make sense if things change or if they don't change. Okay, so again, red, and we got blue. So we got 5 over 5 plus y, and then we get y over 5 plus y. And then we come back to this statement here. It says that the probability that the first counter she takes is red, and the second counter is red. So red and then red. So red and then red is going to be 1 over 9. So we get 1 over 9 as our final probability. Okay, so what does that mean for us? Excuse me. So what does that mean for us? Well, remember what we said? If our probability of red and then red is 1 over 9, it means that we are multiplying. Okay, so we would start off by multiplying our probabilities together. So 5 over 5 plus y times 5 over 5 plus y has to equal to 1 over 9. So let's multiply. We have 5 times 5 is 25. And then on the bottom, we have 5 plus y times 5 plus y. And that equals to 1 over 9. And again, this part's, we're just combining so many different topics. So I actually quite like this question. 5 plus y times 5 plus y, that gives me 25 plus 10y plus y squared is equal to 1 over 9. And again, just like in the previous question, okay, I'm going to cross multiply. I'm going to multiply this denominator up here, and I'm going to multiply this denominator up over here. So 9 times 25 is just equal to 1 times 25 plus 10y plus y squared. I'm just going to write it as y squared plus 10y plus 25, just to save ourselves some time here. Okay. Are we all good on why we're allowed to do that or why we're doing this? Yeah? Okay. So 9 times 25, that's going to be what? 4 times 25 is 100, 200, 225 is equal to y squared plus 10y plus 25. We're going to subtract 225 from both sides. So we get y squared plus 10y minus 200. Okay. So we need two numbers that multiply to negative 200, add up to positive 10. So we know those numbers are going to be positive 20 and negative 10. So positive 20 and negative 10. And we're going to solve this quadratic equation. So we can see here that we'll get y is equal to negative 20. And from here, y has to be equal to positive 10. But we have to reject this answer. And the reason is because we cannot have a negative number of counters. We cannot have a negative number of counters because remember we said that we have y blue counters, so we can't have negative 20 blue counters. Okay, so we have to reject that answer. All right. So if we're taking a look at our question that was asked at the beginning, how many blue counters are in the bag? Well, we said here that y is equal to 10. We said that y blue counters is what we need. So therefore, we have 10 blue counters. Okay. So kind of a tricky question. It involves quadratics, it involves probability trees, uh, it involves solving quadratics. Okay, so lots of different concepts all loaded up into one question. Maybe what I'll do is I'll put one last one on the screen that will be again just as difficult. Um, and then we'll call it a night. I'll put that last question up on the screen, and maybe this is a question that you can kind of verify later on. I'll post that. I'll post the worksheet with the answers. Again, thanks to Math Genie for providing all of these fantastic resources for us to work with. I'll put this last one up on the screen here, and then you can just take a picture of this and maybe work through it on your own. Okay, so you can take a picture of that if that's something that you want to work through tonight. Then check your answer on the Google Classroom. Excuse me. But yeah, other than that, how are we feeling? Are we feeling a bit more ready in terms of probability? Hopefully you guys were able to find some value out of this. Excellent. So yeah, thanks again for coming out, guys. I said I wouldn't go for as long tonight, but here we are, an hour and a half later. So yeah, but I'm glad it was able to help you guys out. Again, feel free to ask myself or any of your other teachers at school for any clarification. So thanks for coming out. Have a good night, guys. We'll see you next week.